This is problem 4-75. It's on page 202. Air is contained in a variable load piston cylinder device equipped with a paddle wheel. Initially, the air is at 500 kilopascals and 27 degrees Celsius. The paddle wheel is now turned by an external electric motor until 50 kilojoules per kilogram of work has been transferred to the air. During this process, heat is transferred to maintain a constant air temperature while allowing the gas volume to triple. Calculate the required amount of heat transfer in kilojoules per kilogram. So they're asking us for the specific heat transfer, not the total, because we don't have enough information to find out how large this system is and therefore how much mass of air is in the system. Okay, now, actually I don't know why I'm drawing that, I don't need that. So heat is transferred to the air, and that's what we want to find out. There's also a paddle wheel where specific shaft work is delivered to the system in the amount of 50 kilojoules per kilogram. So here's the piston. The system is just the air in the system. The system will move from state 1, where the pressure is 500 kilopascals. The temperature is 27 degrees Celsius, which is 300 Kelvin. It'll move to a new state. And notice we don't know the pressure in state 2 because we're told that it is a variable load piston cylinder device. So the pressure in state 2 is unknown. What we do know, however, is that the volume in state 2 is 3 times the volume in state 1. And we were told that the temperature remains constant. Now, in order to find out the amount of heat transfer, and well, we can't do this, right? This is the total heat transfer. We'd have to know the size of the system. But we should be able to figure out the specific heat transfer, the amount of heat that's added to each kilogram of the air in the system. By the way, that's state 2. Okay, we don't know the pressure in state 2, but that shouldn't keep us from solving the problem. Now, the way to think about this is to track energy. We're just energy accountants, really, is all we are. And what's happening here is there's two energy flows. There's two deposits into the bank account, basically. Okay? There's the heat input and the work input. And both of these tend to deposit energy into the system. Now, are there any withdrawals? Are there any places where work is flowing out? Well, actually, yes, there is. There's work flowing out there, and it's boundary work. And so we'll have to account for this energy flow as well. We can't just neglect it. All right, so let's see what we've got. Let's write down the energy balance. Energy in less energy out is basically deposits minus withdrawals equals the change in the energy of the system. In other words, that'll deposits and withdrawals change your account balance in the bank. Same thing here. This is just an energy bank instead of a money bank. Okay. So let's put some more detail to this. How do we have energy flowing in? Well, there's two forms. In fact, let me divide both sides by the amount of mass. So we're talking about specific properties, per unit mass properties, in other words. So, you know what, actually I did that later. Let me be consistent with what I did in the PDFs that you're probably looking at now as well. And remember that you can download all of these once the homeworks are submitted and see what you did right or wrong. Let me go with a full equation. We'll take care of the mass later. All right, so anyway, energy in, shaft work comes in. Notice I don't have the little arm on it, so I'm talking about the total work, not the specific work here. Where else? Well, there's also heat transfer into the system. Let's make it explicitly Q in, but we've got boundary work that comes out of the system. And how does the system respond? Well, the amount of energy in the system changes. What form? What form of energy changes? Does it start moving or something? Well, no, it's just thermal energy. Remember, the system can only contain thermal energy. So this would be a delta capital U type of term. Okay? All right. Now, on this side of the equation, we could use M delta small u, which then we could expand to M CV delta T. So that'll be our approximation for the right-hand side. And this should work out well because notice the temperature in state 1 equals the temperature in state 2. So what does that tell you? Well, that tells you that the change in energy of the system is zero. Does that make sense? Well, wait a second. We had two deposits, one withdrawal. The system got bigger, and yet you're telling me the energy of the system remained the same? Yes. The energy content of an ideal gas depends only on its temperature. Since the temperature remained constant from state 1 to state 2, the amount of money in the bank, if you will, or energy in the system remained constant. It did not change. Well, okay, you can see that. If we're going to find Qn, if that's our unknown, and of course we know this basically, then we better somehow find the boundary work. So let's approach that next. Boundary work is always the integral from state 1 to state 2 of PdV. But we always try to avoid integrating this if we don't have to. There's a nice summary at the end of chapter 4, and anytime you need boundary work, you should go there and see if there's an equation that will allow you to calculate boundary work. You may or may not end up using it, but it's good to know. Anyway, there are two. If you go to page 195, you'll see under heading 4, there's for isothermal processes of an ideal gas, P1 V1 natural logarithm V2 over V1, which is the same thing as MRT, and they've got T naught indicating the temperature is constant, natural logarithm V2 over V1. So we can use this equation, hopefully, to calculate the magnitude of the boundary work and solve for this piece. Then we'll be able to rearrange. Now, I don't know the amount of mass in the system, so the only thing I can really get is the specific boundary work, which is the total boundary work divided by the total mass in the system. Now, I'm going to use, let's see, what did I use? I used the RT because we've got the temperature in state 1, and it's just easy to use. So if I move the mass to the other side of the equation, the next term would be the gas constant, 0.287 kilojoules per kilogram per Kelvin. The temperature, which is 300 Kelvin, as the Kelvins go away, natural logarithm V2 over V1. Well, we know something about V2 and V1. We know that V2 is 3 times V1. So if we plugged in 3V1 over V1, we would just get 3. Okay? So this would allow us to calculate the specific boundary work, and it will be in kilojoules per kilogram, which is exactly what we expect. Anyway, this comes out to 94.5905 kilojoules, if you want that many decimal places, per kilogram. And so that takes care of the boundary work term. Well, almost. Notice this is the total energy equation. I want the specific energy equation. Let's go ahead and solve for this, for Qn, and we'll divide by mass all at the same time. Or let's do it this way. We'll expand the term so that this is the same thing as Qn. If we move the boundary work to the other side, it would become a positive quantity, so plus, well, it's understood, mass, specific boundary work, but the shaft work will become a negative thing. Okay? Now, of course, we can cancel all the masses and calculate Qn. So boundary work, 94.5905. I won't write down the units because they're the same. Shaft work, 50. I guess I will write down the units. Kilojoules per kilogram for both. And so when you take that difference, you find that the specific heat input, Qn, let's see, I don't really have room for it. Let's put it, I guess here. Qn, just the difference between these two, is 44.59 or so kilojoules per kilogram. So there's the answer we were looking for. That's how much heat transfer we need. 50 kilojoules per kilogram of the boundary work comes from the shaft work. The other 44, and well, 0.6, comes in from heat transfer, and that allows a boundary work to occur of 95 or so kilojoules per kilogram.